Wave functions, energy levels, and particle in the box. We now have a lot of backdrop laid to start talking about more complicated topics in quantum mechanics. We eventually would like to be able to have a way to describe how an electron moves around in a hydrogen atom. However, this is an extremely complex problem, even for the physicists who worked on it a very long time ago. And so they started by using a model, which instead took an electron and put it in a box that it couldn't get out of. And they let that electron move in that box. This model, or kind of conceptual idea, is called the particle in the box model. And it allowed theoretical physicists to determine a methodology for calculating the exact movement of an electron in a hydrogen atom. So we're going to start by describing this today, and then when we move on and we're discussing this in terms of a hydrogen atom, even though we're not going to do the math behind it, hopefully the kind of storyline will be complete. So what are we going to do? In this video, we're going to go a bit further into the mathematics of quantum mechanics. This is generally not needed if you're a biology major, but if you're going to go into chemistry or physics, it should be of great interest to you. If you have to take physical chemistry, should definitely be of great interest to you. Now, if you're an engineer with a significant math background, you might just find it interesting and be able to pick it up and spend some time on it. So we were going to define a wave function, and we're going to describe the particle in the box model in terms of this. We'll discuss something called a Schrödinger equation and see how energy levels in this model are determined. You're absolutely not required to replicate the math that we do here, or any of the differential equations that I'm going to show you. However, you'll use the equations that I show you here and for the Bohr model in other problems. And so it's worth having this as a backdrop moving forward. Now, before we get into the mathematics, let's make sure that we know conceptually where we are at. We know that small particles have wave-like properties. We also know that we can describe waves with equations. So that's all review. So the new piece to this is, well, if we can use equations to describe waves, and we know that we know that matter are waves, we can use equations to describe matter. So let's first look at a concept here in animations. In letter A, we see what we would think of as if we were thinking of an electron as a particle, complete, moving around. We see it going back and forth in the box. However, we know that particles of this size are described by waves and that they aren't just a particle like this. And so let's look at what this would look like. If we look at B through D, this shows us a difference. This shows us a wave. Now, what are the differences in B, C, and D? So you can see that the amount of times that the wave goes through a wavelength is different through B, C, and D. These are different energy levels. And this descriptions of different energy levels is what we're going to be talking about here. So we're going to start moving into that as we discuss the mathematics of the process. But for this slide, kind of look at the difference. And you might also want to think about the difference if you play musical string instruments. You can think about that too. Now, note that the more wavelengths that you get within the length of the box, the higher the energy of the particle. So B is of a much lower energy than C, which is of a much lower energy than D. Now, if these are waves, then that means that we should be able to describe them by an equation. And in fact, we can. This equation is called a wave function and is the equation that describes the movement of a particle. We use the symbol psi to denote this equation. Now, different particles have different wave functions. So a particle in a box isn't described by the same wave function as a hydrogen atom's electron or a helium's atom electron. So the process that we're going to step through today is just for a particle in a box. Later on, I'll show you the results of the hydrogen atom as well. So the setup model for the particle in the box is that when you put an electron in between two walls of an infinite potential energy. So what does that mean? It means you put the electron in a box that it cannot get out of. So the infinite potential energy part of it is just saying it is not able to escape from the box. If you do this, only certain wavelengths are going to be allowed. An easy way to picture this is if you think about tying a jump rope on one end and then trying to make a standing wave pattern by moving the jump rope. If you do that, you'll see that you can make the patterns above and nothing else. Now, of course, you could probably make some terrible patterns that aren't patterns at all, but that's not what we're talking about here. So this brings us back to the idea of quantized energy that we've talked about before. The electron is to be allowed to be in one of these particular sets of energies and not in between. And each of these is described by psi, or the wave function. Now let's introduce another quantity called psi squared. Now if psi is the wave function, that means to get psi squared, you simply square the wave function. The wave function itself doesn't have a physical interpretation, but psi squared, or the probability density, does. It tells us the probability of finding a particle within a given space. Here, I now have both the wave functions and the probability densities for the different particles shown. So let's look at each one a bit closer and use an extremely simple example, one that almost has no physical meaning because it's so simple, just to get across the idea of how the probability density can be used. Here we're going to have an example using the idea of psi and psi squared. But because wave functions are really complicated, we're going to not do that for any of the real wave functions and instead just do it for the simplest one possible, a number. So let's take our number, 0.44 centimeters cubed, and we can graph it. So that is our function. Now you might say it's a number, not a function, but it's still a function. So we'll graph this. Now, if you want to know what that function is squared, we need to square it. So if you take 0.44 and you square it, you get 0.2. That's our psi squared. So we could graph that as well. Now let's say we want to know the probability of finding a particle within 3 centimeters cubed. We would take the integral, for those of you who know calculus, or for anyone else, we would just take the area under the curve and find that value. So because I picked the math to be relatively simple here, we'd have 0.2 times 3, which is equal to 60%. Now, obviously this isn't the equation for an electron. It's not going to be described by a simple number. But it does show you how physicists and chemists are able to do these calculations, so that when I flash up some real formulas and results on slides, you know where they came from. Even though, once again, I am not asking you to replicate this, I'm not asking you to repeat this, it's good to have the story background. So let's answer some quick questions. Given that psi is some function, what is the sign going to be? Take a moment and answer this for yourself before I answer it. So there's no reason why this can't be both positive and negative. And in fact, if you're defining 0 as kind of the middle of your wave, well, it's going to be both. And there's no reason why this wouldn't be true. Now, think about the probability density. Given that the probability density is the square of psi and denotes the likelihood of finding an electron in a particular place, what does the sign of that have to be? It's psi squared, and anything squared, assuming real numbers, are going to have to be positive. And so psi squared is always positive. We'll take a minute and go back to our picture so we can see this too. So before I move on to talk about nodes, just quickly confirm what we decided on the last slide, that psi can be both positive and negative, while psi squared can only be positive. Now let's talk about a special place that appears both in the particle in the box model, as well as in the hydrogen atoms. A node occurs when psi is equal to 0. If psi is equal to 0, what is the probability density must be equal to? Well, if the probability density is psi squared and psi equals 0, the probability density must also be 0. And if the probability density is 0, that means that the chance of finding an electron at that place is 0. So this means that no electron is ever found at a node. So particle-in-a-box wave functions are going to have a certain number of nodes. And that's always going to be n is equal to 1. And that's a good thing to know as a general rule. If you're ever in a situation where you're learning about particle-in-a-box model and you're going to be tested very heavily on it, to know that your nodes is equal to n minus 1. This is going to change depending on what wave functions and what models you're talking about. So don't take this to be like a universal always for every wave function. Now we need to talk about something called the Schrödinger equation. This is something that allows scientists to find both the wave functions and the energy of the particle. We won't be doing the actual math on this at all, but you should have a basic understanding of how it exists and how scientists apply it. This is a differential equation, and so the math goes well beyond the scope of the general chemistry material that you're going to cover in this class, and you'll cover it if you do upper division chemistry courses like physical chemistry. However, there are still a couple of things that we can go through. First off, what is the little hat on the H symbol? So this is called an operator. An operator is just something that operates on a function to yield a new function. So in other words, it's something that changes the function a little bit and gives you a new function. So if we look at what we have on the other side of the equation, we get energy times the wave function. So if we try to turn this into more English, we have an operator which operates on the wave function to give us the energy and the same wave function. Now, again, just to illustrate the topic, let's put up an overly simplistic example that doesn't have anything to do with sort of physical meaning, but can be helpful if you're interested in this sort of material. You're not going to have to replicate the math. So from here, you can then kind of extrapolate and at least understand a bit of the idea about what the scientists are doing to get the answers on the following slides, rather than it being like hand wave magic, here's the answer. So I will say that this concept is best explained with derivatives, and I'm aware that there's a few of you in the class who haven't had calculus. I do apologize for using the calc here to help explain it, but sometimes it just isn't avoidable, and I'm not going to test you or make you replicate this anyways, so I'm going to go ahead and stick with it. But for those of you with even a small amount of calculus, I think it'll help you understand. So we have a wave function of sine equals 2x, and we operate on it with a double derivative. So if you put it in, just for fun, I also put a negative on it. So if you go ahead and do this, and you take the double derivative of this, you get back 4 sine 2x. So here you can see that you get back a number times by the original equation that you started with. You started with that sine 2x, and you get it back. So this is how the Schrodinger equation works in an overly simplistic way. Now, here just for fun, I've put up a Hamiltonian for a particle in a box. If we solve this, remember if it's a differential equation, and we get both psi and e for the particle in the box. For those of you who know differential equations, give it a shot. See if you can figure it out before moving on. However, this is not something that in any way you will be required to solve. So I just want to show you the results, and I wanted to show you the Hamiltonian in case you care. And if you don't, you can simply move on. So waving my hands and magically solving, I get the wave function and I get e. This is the result of solving the equation for the wave function and the eigenvalue or the energy. We can use these to solve for the energy levels of the particle in the box by filling in numbers. So n is the energy level, so it's just an integer that we're solving for. And we also have L. L is the length of the box, so this would be something that you would know by setting up your model. This is all getting a little vague and a little abstract, so let's pull it back to an example problem. I want you to use the particle in a box to estimate the value of the energy of an electron in an atom. Now, this won't be the exact value, of course, because we're using a particle in the box model, and that's not the same as the three-dimensional hydrogen atom. But it can give us an example of kind of showing how we're building up to get to hydrogen atoms and atoms beyond that. So we're going to use the formula for the energy that we used in the last slide. We'll use this to solve for the energy. So let's fill in our values for n, m, and L. M is the mass of the electron, so that's a known value that we can plug in. N is the energy level, since we're doing the first energy level, it's just 1. And L is the length of the box, which is given in the problem. We fill all of this in, and one little thing that we have to make sure we do, we have to convert from picometers to meters, and that's because of that H. H is the same H that we've been talking about all chapter, and we can plug that in. And this gives us our final value in joules. So this idea of going through and finding the wave function, and then finding the energy levels, and then using the energy levels to do things is what we're going to see happen in the hydrogen atom. And the hydrogen atom will just give you the results, but it's useful to see that this is where it came from. So wave functions are used to describe the movement of particles. You need to know that. If you square the wave function, you get the probability density. You need to know that too. And this is used to determine the probability of an electron being in a particular space. When we get to orbitals, this is going to actually be how we get the orbitals, is by using these wave functions. Now, using the Schrodinger equation, we can solve for both the wave function and the energy levels of the particles. And then we can use these results to solve for the energy levels on each model or each energy level of a model of an electron. This was a little more in depth than what we're going to do with any of the other models. And it's good to have that backdrop as we head into the hydrogen atom and we head into orbitals and we head into all of these concepts where we're just going to say, and don't forget, this is solved for by using the Schrodinger equation, even though we're not going to be doing it.